This video is going to cover Castigliano's method for frames. So to start with, we have just a basic U-shaped frame where A is a roller and D is a pin. And we have fixed joints B and C, and we have a linearly distributed load across member BC, which is 55 kilonewtons per meter. We have the frame being 8 meters tall and 6 meters wide. What we want to find is the horizontal displacement at A. So it being Castigliano's method, the first thing that we need to do is actually put over at A, we need to put an applied load P. So we need to apply P first. So I applied P horizontally because we want to find the horizontal displacement at A. Next up, what we want to do is probably find some reaction forces. So we're going to have AY. D is a pin, so we're going to have dy and then also dx horizontally. So if we start by, say, summing the moments about D and set it equal to 0, taking counterclockwise to positive, we're going to have that dx and dy are both acting at pin D. So those aren't going to be here. And also P is acting in line with D. So P is also not going to act. So the only thing that we're going to have is then going to be AY. So that's nice. So we're going to have AY is going this way around. So that's going to be negative. So negative AY times a distance of 6 meters. Then we have our distributed load on top, and he's going this way, so that's going to be positive. So plus 1/2 times the base of 6 meters times the height of 55 kilonewtons per meter times the distance of his centroid, which is roughly over here. So that distance is going to be 1/3 the base of 6. And if we solve for that, we're going to get that AY is equal to 55 kilonewtons going up. Now, if we sum the forces in the y direction and set it equal to 0, we're going to get dy, because we have AY going up, we have dy going up, and we have our distributed load, are 1/2 times the base of 6 times the height of 55 kilonewtons per meter. So we'll get that dy is equal to 110 kilonewtons going up. Now dy is twice as much as AY because dy is at the bigger end of the triangle than AY, so that makes good sense. And if we sum the forces in the x direction and set it equal to 0, we got P going positive, we have dx going negative. So therefore, dx is equal to P. But remember, definitely going the assumed direction. So now that we found our reaction forces, we need to start making some cuts. So cut number 1 that we're going to take, we need to cut along our vertical member here. And we're going to measure y from the base going up. Cut number 2, we got to go into our horizontal member here, and thankfully the loading is all the same. So we're going to take a cut right there. Again, we're going to take x going from left over to right. And then now that we've got a third member, we're going to need to make a third cut over here. Now we could technically go top down, but that seems kind of silly. So again, we're going to take y going up. So those are our 3 cuts in our 3 different directions. So now we need to draw some free body diagrams. So for cut number 1, or section 1, for section 1, we're going from 0 to y, where y can go all the way up to 8 meters. So from 0 to y to 8. Let's draw ourselves a little free body diagram of what's actually going on over here. So we've got a little section of a very ugly beam there. We got a prettier section of short stocky column. Don't forget, at the bottom we have our load P, and we've also got AY. Now AY is 55 kilonewtons, and we said Y was this distance here, and then we've also got our internal shears, normals, and moments. And of course the only one we care about is the moment. So if we sum the moments about the cut and set it equal to 0, taking counterclockwise to be positive, we've got positive m, that's good. We got plus p times the distance of y, and our 55 kilonewtons is acting right in line with the cut. So that's it. Actually, that's all for our moment equation. So we're going to get that m is equal to negative p times y. So del m, del p, the partial derivative of m with respect to p is negative y. And when you set p equal to 0, you get a moment equation of 0. Well, that's fun. Moving right along, we're going to have section 2. So section 2 is going to be a little bit interesting because we can't just ignore the vertical part. So we actually have to include, for section 2, we have to include this whole member vertically, and then we're going to cut horizontally. So it's actually that whole thing there, that whole L branch. Kind of annoying, but really not that bad. And x is going to go from 0 to 6. So we have 0 to x to 6 meters. So again, let's draw us a pretty picture. Now we're going to shrink it just some because nobody actually cares about all of that vertical height there. So just assume that this bad boy is a grand total of 8 meters tall. So there's P. This is 8 total meters right there. Just go with it. This is x. Don't forget we've also got AY, who we said was 55 kilonewtons. Awesome. And then we've also got our distributed load. Our linearly distributed load. Now, what's his height? This always gets fun. Effectively, what we're doing is creating a similar triangle, or you could think about it in terms of slope. So the slope is rise of 55 over a run of 6. Okay, or if we want to think about it in terms of similar triangles, we've got a height of 55 over a run of 6. And we want to find, let's say, this random location here, we're going to call it y. And this is x, the horizontal distance that we're making the cut. So effectively, this point right here is y. So if we're doing this, we have a height of y over a distance of x is equal to 55 over a distance of 6. So you get that y is equal to 55 over 6 times x. So in case you're ever wondering where that came from, it's literally just similar triangles all over again. So the value for this spot is 55 over 6 times x. And then don't forget we got internal shears and normals and moments. So there's our free body diagram. A little bit more work than the other one, but same thing. We're going to start by summing the moments about the cut, set it equal to 0, counterclockwise being positive. So we've got m to start with, he's definitely positive. Then we've got our 55 kilonewtons over here, he's going this way. That is not the good direction. So we have minus 55 times his distance of x. We got P. P is going to be going that way around. That's positive. So we've got plus P times a distance of 8 meters, right? So that's wonderful. Then we've got our linearly distributed thing, and he's going this direction, so that's positive. So we've got plus, we've got 1/2 the base of x, the height of 55 over 6 times x, times the distance from its center, which is 1/3 the base being x. Well, that's delicious. So this boils down to m is equal to 55x minus 8p. We're going to do all this math all together. Minus 55 over 36x cubed. Now he doesn't look exactly exciting, but he's not too bad. Del m del p, the partial derivative of m with respect to p, is just -8. It's really not bad at all. If you set p equal to 0 and solve for a moment equation, we're going to get 55x minus 55 over 36x cubed. So that's not too bad. Moving on to section 3. Section 3, we're not going to continue going around. No, we're going to turn the other way, and we're going to start from the bottom and work our way back up. So we're actually only going to have this piece. That's a lot better. Yes, doing the corner gets not quite fun. So for section 3, we're going from 0 to y, and y's total could be up to 8 meters, just like before. We need to draw ourselves a nice, beautiful little diagram. Short little stocky sucker there. Then we've got dy. dy was 110. We have dx. We said dx was equal to p. So that's conveniently very similar to what we've seen before. We have a height of y. And we have shears, normals, and internal moments. So wow, this is looking pretty similar. If we sum the moments about the cut and set it equal to 0, taking counterclockwise to be positive. Again, the 110, he is acting in line of that cut. So he's not going to be a part of this. We just have m, and we have minus p times y. So m is equal to p times y. That's wonderful. Del m del p, the partial derivative of m with respect to p, is equal to just y. And if you set p is equal to 0, you get a moment equation of 0. So that's fun. Now remember, we wanted to find horizontal displacement at A. So we're doing a deflection effectively. So what we're going to do is we're going to take the horizontal displacement of A. Remember, this is going to be times EI, or divided by EI, all this stuff. So this is equal to the integral for section 1. Section 1 is from 0 to 8. So 0 to 8 del m del p, which was -y, times m, which is 0, dy. All this is over E and I, but I is very specific to its member, and its member is member AB. So we're looking at 200 blah, 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 blah. So this is specifically I of AB. Not that it matters, because m was 0. But anyway, moving right along. Then we've got plus the integral. This is for section 2. Section 2 is for x. It goes from 0 to 6. And we said for our del m del p, it's -8. And then m was a little bit more than that. Okay, so we have -8. And our m equation, 55x minus 55 over 36x cubed. 55x minus 55 over 36x cubed. Dx, remember this is over E I, BC specifically. Plus, we've got the integral. This is for section 3, and we said it's going from 0 to 8. Del m del p was y, and m, 0. dy, gotta love it, over e times I, CD. So I love the part where that's 0 and that's 0, and if you take the integral of 0, you're going to get nothing. So that's wonderful. So now we're just literally left with this guy. So whereas the problem seemed a little bit difficult, actually boiled down to something simple. So we're really just looking at the integral from 0 to 6 of, we're going to kind of put all of this into here. We have in solve, well, we'll just kind of solve it. You've got 8 times 55, and that's going to be an x, so it's going to be x squared, so then you're going to divide by 2. So we've got 440, but ooh, it's negative, so negative 440 over 2, that's 8 times 55, x squared. A minus and a minus is going to be a plus. 8 times 55 again was 440 over 36, but 36 times 4 is 144, and that's going to be to x to the 4th. And that's going to be across 0 to 6. All that over EI. Let's not forget the 1 over EI part. We're going to come to the EI part in a bit here. So then we get a value of negative 3,960. This is kilonewtons, meters cubed. But over E was 200 gigapascals, and the I that we actually care about, so E is 200 gigapascals. We only care about IBC, which is 300 times 10 to the 6 millimeters to the 4th. So 200 gigapascals. So 200 giga is times 10 to the 9th. Pascals are newtons per meter squared. And then that's E. We said I was 300 times 10 to the 6 millimeters to the 4th. Now, be careful with your units. We got kilonewtons, we got meters, we got millimeters, we got newtons. So there are 1,000 newtons in a kilonewton, and that's going to go ahead and cancel out my newtons here and my newtons here, my kilonewtons here and my kilonewtons here. And then I'm actually, if we take this guy, he's divided, so he's going to be up top. So that's millimeters squared, or meters squared up there. So that in total is meters to the 5th over millimeters to the 4th. Kind of nasty. So times, there's 1,000 millimeters in a meter. And I don't think anybody's asking for how many meters of deflection there are. So let's maybe do this to the 5th. That's going to cancel out all the ones to the 4th and all of the meters to the 5th. We're going to be left with millimeters up here. So that's kind of nice. We're going to be left with our millimeters. So what do we get when all is said and done? We get negative 66 millimeters for the horizontal deflection at A.